So now these are the structures of the ligands. So this is the porphyrin ring, and this is corin ring, this is chlorine. So all these are the structures of the ligands which play a very important role in biomolecules. Now let us see the basic structure of a porphyrin ring. A porphyrin ring is a large organic molecule made up of 4 pyrrole units. A porphyrin ring is a large cyclic organic molecule which is made up of 4 pyrrole units. This is one, this is another one, this is the third one, and this is the fourth one. So it has 4 pyrrole units. These 4 pyrrole units are connected to each other through a methane bridge. So this is the methane bridge. See, this is one pyrrole ring and this is another pyrrole ring. This is connected to each other by one methane bridge. When you look at the structure, we can see 4 nitrogen atoms present in this macrocyclic system. And when we look at the double bonds, we have 11 double bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay, so when we look at the double bonds, we have 11 double bonds. But for aromaticity, we don't consider the inner pi electrons. There are 2 pi electrons here in this pi bond, and there are 2 more pi electrons in this pi bond. We don't consider this inner pi electrons. Okay, so when we look for the aromatic pathway, we only consider the peripheral, that is the outermost double bonds for aromaticity. So in that case, only these 18 electrons, this 2, 4, 6, 8, 10, 12, 14, 16, 18, only these 18 electrons are taken into consideration. And therefore it follows 4n plus 2 rule, and it shows aromatic character. Because of this arrangement, it is planar and highly conjugated. And this extensive conjugation is very important because it is responsible for many of the characteristic electronic and spectroscopic properties of porphyrins. Another important feature is the central cavity. This cavity is surrounded by nitrogen atoms so that it can accommodate a metal ion. Okay, so when any metal ion comes and accommodates this central cavity, it is called as metalloporphyrin. So the important things to remember here are, it contains 4 pyrrole units. Pyrrole links are connected by 4 methane bridges. It has 4 nitrogen atoms, and the resulting structure is planar and aromatic. And the central cavity can bind to a metal ion. So these are the important points to remember in case of porphyrin ring structure. Now we will see the different types of hydrogen in the porphyrin ring. Initially, when you look at the structure of the porphyrin ring, it may look little complicated, but here in this diagram, I have shown the different types of hydrogen in different colors so that it becomes easy for anyone to read this. Porphyrin ring has 3 types of hydrogen. One is called as mesohydrogen, the second is beta pyrrolic hydrogen, and the third is the inner NH hydrogen. Okay, so in a porphyrin ring, there are 3 types of hydrogen, and I have tried to show them in 3 different colors. This green color, the position H5, H10, H15 and H20, they all are called as mesohydrogens. So these forms one set of hydrogen, and the hydrogens which I have shown in orange color here, which is attached to the pyrrole rings, all these are called as beta pyrrolic hydrogens. Okay, and we have 8 such beta pyrrolic hydrogens. Here for mesohydrogens, we have 4 mesohydrogens. And for beta pyrrolic hydrogens, we have 8 beta pyrrolic hydrogens. And the third type of hydrogen is the inner NH hydrogen, which is connected to the nitrogen atoms. 2 such inner NH hydrogens are present. Okay. So when we look at the types of hydrogen, there are 3 types. First one is the mesohydrogen, second is the beta pyrrolic hydrogen, and third is the inner NH hydrogens. Altogether, there are 14 hydrogens in total. There is 4 mesohydrogens, 8 beta pyrrolic hydrogens, and 2 NH hydrogens. This classification is very important when we discuss the NMR spectroscopy, because these different hydrogen environment will give rise to different signals. This is very important when we see proton NMR spectroscopy of porphyrins. We just saw the different types of hydrogens. When the two inner hydrogen atoms of the porphyrin ring are replaced by a metal ion, the resulting complex is called as a metalloporphyrin. So by now, all should be clear with what is metalloporphyrin. So this is the same as I have told earlier. When the metal Fe in +2 state, it binds with the porphyrin ring, it forms the complex heme. This is very, very important. We also saw the structures of chlorine and chlorine. When the ligand chlorine combines with the metal ion Mg in +2 state, it forms the complex chlorophyll. We would have seen all these in many places, but the ligand and the metal system here is chlorine and magnesium in case of chlorophyll. And in case of vitamin B12, the ligand is chlorine. It binds with the metal cobalt in 3+ state. And similarly, there is another ligand called hydrochloroquine, which combines with nickel in 2+ state, and it forms coenzyme F430. The interesting thing is these macrocyclic rings can coordinate with different metal ions, and the resulting complex have very important biological functions. If we look at the table, there is a simple relationship here. We have a macrocyclic ring system, the metal ion, and the corresponding biological complex. These examples show how the combination of a macrocyclic ligand and a metal ion gives rise to biologically important molecules. Now that we can understand the structure, the hydrogen environment, and the biological importance of the system, we will now move to the spectroscopic details of porphyrin.